Good morning, everyone. This class is about an example of sparse autoencoder, where we will use sparse autoencoders to remove noise from the dataset. So basically, kind of a denoising application of sparse autoencoders. So if you look at the program here, I'll just maximize this. So if you see the autoencoder program that I have made, you will find that I am using the same MNIST dataset, but this time what I have done is I have loaded the pre-trained, not pre-trained, the pre-loaded dataset which is available in MATLAB, which is the digit train cell array data. If you remember in the previous example, what we have done is we have loaded the 4D data and then we had to convert this into a cell array form, which was then given to the autoencoder. But if you want to avoid that particular step completely, what you can do is you can load the handwritten data set directly as a cell array, and for that you have to use only this command, digit train cell array data. And as you can see, if you double click on each of the cell arrays, the image will get opened. And please remember that you will find the values inside each of the pixels scaled in the range of 0 to 1. If you use this image for viewing, it will show up just fine. Uh, how these values are arrived at is simply by dividing each pixel value by 255. So you get values between 0 and 1. Okay. So there is no particular need to convert it into pixels to do any kind of processing. MATLAB works very well with this scaled values itself. So that is the first step, loading of the data. Second step is how to train the autoencoder. If you look at this second step, you will find that I have used 300 hidden neurons, and the train autoencoder function is this. And you can see directly that I only have to specify the training data, because according to autoencoder theory, the input equals to output. So I need not specify any output explicitly. So what you have here is the input, the number of hidden neurons, how many number of epochs you want to run it, and the L2 weight regularization and sparsity regularization terms, as well as the sparsity proportion term. These terms we have seen in the previous video on sparse autoencoders. I also do not want to scale the data anymore, so I will leave it as false. Once that is done, I will um, have a tested a trained autoencoder, and it will be a network of the name Autoenc. You can have any other name for this also, does not matter. And you can see, if you just put your cursor on it, it will just show you what are the parameters of this autoencoder class. You can also look at each of these properties one by one by simply using the dot indexing. So now you can see the encoder transfer function and the decoder transfer functions are both log sigmoidal, and how many encoder weights you have, how many biases you have, how many decoder weights and biases you have, all of this will be shown here itself. Now what we will do is we will go into the testing phase, where we are just plotting the testing images. Some random 20 testing images are being pulled out and are being displayed. That is what happens in the step 3, and you can see here on the right hand side, what you see are the randomly drawn images from the test dataset. The fourth step that we are looking at is trying to find out what kind of reconstruction error is generated. So if you look at this, what we are doing is we are simply using the predict function, predict of autoencoder object, comma, testing data. Each element by element in the cell array is being passed to the predict function, and the output is available to me as a testing data reconstructed cell array. So this is also a cell array, and the input was also a cell array. And if you try to reconstruct that uh, particular test dataset, I'm trying to recreate the same, exactly same objects. If you look at this, at the top and the bottom, you get the same thing: 3 3 8 8 9 9 6 6 1 1, and so on. So you can see the reconstruction at the bottom is slightly little more hazier. You can improve this by increasing the number of neurons in the hidden layer. And the reconstruction becomes worse and worse as you have lesser and lesser number of neurons in the hidden layer as well. So what we have done is we have seen that it's able to reasonably reconstruct the images that were in the test set, and we can also find out how different the actual images are from the um, how reconstructed images are from the actual test set by using the MSE function, mean squared error. So that is the mean squared error function that you see here, MSE of cell to mat testing data minus cell to mat testing data reconstructed. The cell to mat function is required because you cannot subtract two different cells together, because cells are supposed to contain any kind of data. You can make a cell out of any type of data. So first step that you have to do is to convert a cell into the underlying data type that it has got. In our case, it will be a double data type. So first what we do is we convert the cell into its underlying data type and then carry out the mean squared error calculation. So you can see here the mean squared error that you have got is about 0.0135. The better the reconstruction, lesser will be the MSE error. All right. So we have reconstructed the images. Now in step 5, what we do is we will simply try to create a new data set, which is basically composed of noise added to the original test data set. So if you look at this same test images that we had, I have simply added a salt and pepper noise to the dataset. So now you can see there are a lot of black and white dots which are appearing at random places. This is what is called as a salt and pepper noise. So you can see this is being done by using the first few lines of the step 5. You can see here that I'm just simply adding noise by using im noise function, picking up each and every single image and adding the noise of the type salt and pepper, and what percentage of noise has to be added is given by D. So D is set as 0.1, that is roughly about 10% is the limit. So now what happens is that randomly some of the pixels are chosen and they are converted as totally black. Certain other pixels are chosen and they're converted into completely white, and the remaining are left as it is. So that is why you see salt and pepper uh, noise. That's why the name salt and pepper. Some black pixels, some white pixels, and remaining are left untouched. So you can see you display the same thing. You will get the test image itself, but with added noise. Now what we will do is we will try to remove this, and all that you have to do it for removing is simply use the same original autoencoder which you have already trained and pass the noisy data to it. So when you pass the noisy data to it, the result that you will be getting will be the testing data reconstructed noisy, which if you look at this is almost same as the reconstruction that we got for image which had no noise, which basically means that this system is able to ignore the noise that is present in the images. So this is where autoencoders become useful. Denoising is something which these kind of networks are relatively good at. So we will continue with autoencoders in the next video also. We are going to look at stacked autoencoders and how they can be used. Thank you.